Hi there! Welcome to a new physics lesson filled with adventure and discovery. Today, our topic is sound intensity and resonance. Last time we looked at sound waves and how they're made, how they are actually like pressure waves that are longitudinal and can vibrate against our eardrums. And we took a test on how our ears can only hear a certain range of frequencies, which is how many times the waves hit our eardrums. Today we're going to be looking at sound intensity, or rather the amplitude of the waves, and how the power of the waves can actually affect how we hear sound, which is pretty fascinating. So let's jump into it. So sound intensity. What is sound intensity? Sound intensity is the rate at which energy flows through. In this case, sound energy flows through a certain area. So notice we have intensity is equal to change in energy over time over the area, or what we call power, over a certain area. And so, and because sound expands in kind of like a spherical motion, kind of like a drop in the water makes ripples that spread out from the center, we can come up with this equation. Intensity is equal to the power divided by 4 pi r squared, or the area of the circle that it spreads out in. And so here's something that you might see on your quiz. Let's say we have the sound intensity from an explosion is 0.1 watts per meter squared, and we're standing at a distance of 1 times 10 to the third meters, which is pretty far away. But we want to find the sound intensity at a distance of 5 times 10 to the meter squared, so a little bit closer. How would we figure that out? Well, we take our equation. Intensity is equal to power divided by 4 pi r squared, which is the circle area of the sphere kind of spreading out. And so we plug in our numbers. Our first intensity is 0.1, and then we have power divided by 4 pi r, and then r is our distance away, so 1 times 10 to the third squared. So we come out, if you solve for p, you multiply this all together, don't forget to take the square root, and then you multiply it to the other side to undo this division to get p by itself, power by itself. We come up with this really big amount of power from that explosion. But then we want to find the intensity at a distance a little bit farther away. So it's a two-step problem, and so we'd plug it back into our equation again, except this time we plug in for power, and we're going to find a new intensity and compare it to the first intensity. So we take our power that we got from that last equation, divided by 4 pi, and then times the distance, the new distance, which is 5 times 10 squared, so 500 meters away. So you plug that into your calculator, and you would come out with 0.4 watts per meter squared. So that's how much power is exerted upon that circular area at that distance away. Okay, so that's kind of what we're calculating for intensity. And so the audible range for intensity can vary for the human, and it's interesting because it differs based upon pitch, and it also differs not sequentially but at different rates. And so notice that our auditory experience covers this whole area of frequency as well as what we call decibels. Sound intensity, we've come up with a logarithmic scale to measure sound intensity, and so we have decibels over here. Notice that this is kind of our range, and so if you're playing an orchestra, this is kind of the range that you can play a string instrument at, and the vocal range is kind of here. So the highest you can get is over here, and then the highest pitch you can reach is over here, and lowest pitch here, and then the loudest you can probably yell is this much, and the softest you can kind of whisper is that much. Okay, so that's kind of how to interpret this chart here. This is, if you go up and down, that's how loud you can get, how intense the noise is. And then from left to right is the frequency, which is the other thing that affects our hearing ability. And so like I said, we use a decibel to measure sound intensity. Originally we used the bell, but the bell is too big of a measurement, and so we use decibels, okay, which is a smaller increment of sound. And so it's a dimensionless unit, and it's a ratio of two intensities of sound. And so we use it kind of as a relative scale for how intense the sound is. So notice our threshold for sound intensity is between 0 decibels, which is like not hearing anything at all, and then 120 decibels, which at 120 decibels, so notice this over here, that's kind of like a passing ambulance, really, really loud, really, it might even hurt your ears a little bit, but we can still hear stuff. Higher than that, it would cause that ringing noise in your ears. So here's a little video that kind of displays that, the amount of decibels. So cars passing, if you're standing there. This is 1 decibel quieter than that first picture. So you can barely tell the difference between the two. 3 decibels quieter. So it's the same clip, just being played at different decibels. So that's 10 decibels, so now you can really see the difference there. Okay. And so hopefully that kind of gives you a good picture of what a decibel is. Okay, and then our second topic for today is resonance. And so resonance happens not just in sound, but a whole bunch of different things. But it happens when we match the normal frequency, what we call the natural frequency of whatever it is. So this table here, when I tap it or make a noise, it has a certain frequency, it has a certain pitch. That is its natural frequency. If I hit a beaker, right, it's going to have a different natural frequency. And so when we have things at the same frequency, we can cause it to kind of rock back and forth, kind of like a swing. When you're pushing somebody on the swing, every periodic time period, you have to make that push. If you're sitting there on the swing alone, you have to kind of extend your legs and then push back at the same kind of rate, at that same frequency. Otherwise, you won't get bigger and bigger. So same thing here. So here's an interesting problem. If I have 4 different balls and they're all at different lengths except these 2 blue balls, and if the blue pendulum is set into motion, only the blue pendulum with the same length will eventually oscillate with the same frequency. So if I hit that ball and get it moving, eventually the only ball that's gonna also move, eventually oscillate with the high frequency, will be this other blue ball that's at the same length of string, and that's because they have the same length of string, and they're gonna have what we call resonance. We saw this also you might have seen this before in AP Chem, the Tacoma Narrows Bridge. This bridge was built in such a way that because of the wind, it started resonating and swinging the bridge.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's 3rd largest suspension bridge.
So the wind was causing it vibrating at the right frequency over and over again.
Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
Okay, so that was the Tacoma Bridge, and that's why whenever soldiers walk on a bridge, they actually have to stagger their step, otherwise they will also cause the bridge to start swinging. So really interesting thing when we're talking about resonance. I have a last video here that you guys can watch later on your own time that talks about resonance and other objects. You might have heard of people playing a loud enough noise so it breaks glass. And a lot of times that's because of resonance. When you hit a glass and it rings with that certain pitch, that's the resonant frequency, or the natural frequency. And if you play another noise at that same frequency, you can cause the glass to vibrate and start swinging and eventually break the glass, which is pretty cool. Yeah, that's resonance and sound intensity. Thank you so much for joining us, and we'll see you next time.